All right. So, guys, the uh, thing we're working on right now are universal gravitation practice problems, mostly conceptual based here. Number one, Earth remains in orbit around the sun due to the force of gravity. How does the force of gravity exerted by the sun on Earth compare to the force exerted on the Earth, or by the Earth on the sun? So in our simulation yesterday, okay, we were taking just a kind of a gander at how the force changes depending upon distance, right? Farther away, it gets smaller, the force. As we move closer, you can see that the force increases crazy, dramatically. Then we asked if we show uh, the force from the planet as well. Okay, if you bring the ruler out, you can measure them, and they will wind up being the exact same size. Okay, tying into kind of Newton's third law, equal force, opposite direction. So they're going to exert the same amount of force on each other. Now, the smaller object is going to have much more dramatic change in motion, in this case, the Earth. So they exert the same force on each other for number one. All right, so for number one, they exert the same force on one another. For number one, they exert the same force on one another. Okay, next one. So what we need to do for this is if we look at Newton's law of gravitation, okay, it is big G times m1 times m2 divided by the distance between them squared, or the distance between their centers. Okay, some places they may use r at the bottom. Now, big G is a constant value. We wrote that down in our notes, 6.67 times 10 to the negative 11. Now, since that is a constant, we are not going to worry about that, right? Because that can't change. So in our equation, the only things that can possibly change are the two masses and the distances, all right? Or the distance between them. So this is where we would break it down into using what we would call the ones equation. All right, the ones equation. So gravitational force, right? This will be m1. This is m2, and d on the bottom will be a 1, but you also have to square it. So I call this the ones equation. All right, we can take our variables, kind of turn them into a 1, and when they say, okay, if this such and such doubles, what's going to happen to the force, all right, or what happens to this variable? Pretty simple now. It says if the mass of one object doubled. Okay, so again, big G we're pretending is not there because it's a constant. It's not going to change anything. M1, M2. Now, does it matter who you're going to change? No, I usually will just change the first one. So the mass of one of the objects becomes doubled. So we're going to, instead of it being a 1, we're going to make it a 2. We didn't change the other mass, M, right, or M2 here, so that's going to stay a 1. And they didn't tell us anything about distance, so the distance on the bottom is still going to stay a 1. And once you get to this point, we'll just work it out. 2 times 1 is 2, 1 squared is 1, so 2 over 1. So you will be 2 times the original force, the original weight. When you have that, all right, if they're telling us the original gravitational force is 4 newtons, now we're just going to sub it in. All right, that value for F sub G. So it will be 2 times the original value of 4. And this will give us a final answer here of 8 newtons. Okay, so mass of something, of one of them doubles, the weight or force doubles. Okay, now they're saying what happens if both masses are doubled? Well, if both of them are doubled, right? This is our one's equation originally. If both of them are doubled, the masses, well, they're both going to become 2s. So 2 times 2. They didn't tell us anything about the distance, so it stays a 1, and we square that. 2 times 2 on top, 4. 1 squared on bottom, 1. So this is just 4 times the original force. They want to know what the new value is, though, so you'll do 4 times that value. The original value in the problem is 4 newtons. So this 4 times 4 newtons is going to give us a value of 16 newtons. If the masses do not change, but the distance between, all right, distance doubles, what's the new force? All right, masses do not change. So, God bless you, those stay at 1s. Distance, right, is on bottom. So masses stay 1s. The distance, all right, on bottom, is now going to be doubled, so we have to make that a 2. Right? And then we just work it out. 1 times 1 over 2 is 1/2. Correct. I was hoping. Yes. All right. You have to make sure you square that. All right. That is just one tiny mistake that some people might forget. So I'm glad you guys were able to spot that. 1 times 1 is 1 on top, and 2 squared is 4. So you are 1/4 the original force. If the original force is 4, what is 1/4 times 4? It's just 1. Okay, you guys should be able to do this next one. All right, try that real quick. Okay, after you've tried that, what's telling us here, both masses and the distance. All right, so both masses and distance doubled. So here's just your original ones. So if both masses doubled, they both become a 2. And if the distance between them doubles, so d on bottom, we make it 2. And like you guys mentioned before, we can't forget the squared. 2 times 2 is 4. 2 squared is 4. So 4 divided by 4 is just 1. So it's 1 times the normal force, or 1 times the original force. The original force was 4. It's just 4 newtons. All right, now for the next problem, guys want to make sure you're able to do this on a calculator. All right, cell phones don't really cut out for this one. So this is going to show you how to really work with the exponents. So if anyone had me last year for chemistry, you probably had some practice with this when we were dealing with, all right, going from grams to moles and having to use the exponent feature. So our equation is big G times M1 times M2 over the distance squared. Now, they're telling us that all right, a 1 kilogram object, that'll be my M1, okay, is on Earth's surface. Mass of Earth, they give us this value here, that will be our M2. And the radius here, that will be our d. All right, so let's put in all of our information. What is the value for big G again? 6.67 times what? 10 to the negative 11th. Good. First mass, M1, we said is 1. And M2 we have as 5.97 times 10 to the 24th. Yes, very big. And then what do we have on bottom?
6.37 times 10 to the power.
And we just can't forget to square that. So that is sometimes when we're writing exponents and stuff like this is where we have a tendency sometimes to forget to square because we have an exponent as far as like a planet's radius. Now, I'm going to show you guys how to type this into the calculator. Okay, so I want you to do it along with me. All right, there's an easier way than always having to do times 10 to the going like times 10 raised to the whatever the power is. Okay, so also you have to make sure if you're doing it like that, parentheses have to be in the right place all over. So what you're going to do is 6.67. Okay, so type that in. Now, above the 7 button, okay, above the 7 button, you guys should see this right here. Now, it may either, if it doesn't have x to the 1, it should have like that double E right there. It is basically a shortcut to put your calculator, all right, into the times 10 power range. So instead of having to hit times 10 caret and then whatever your exponent is, if you just hit that, not times E, just E. So 6.67, all right, I have to hit second on mine to get to it, and you just want that to show up. Okay, so I hit second, this, got that. After E, you don't put this, no. Okay, you just type the exponent. If the exponent is positive, you just put that number. But if it is negative, then you are going to not put minus, but you will put a negative sign. So you're going to hit negative 11. Okay, then we can go times 1 times 5.97. And then what would I hit? E, right? Not times E, just E. And now what do I type in after E? 24, right? Good. Because that is telling us that's what the exponent is. All right. Yep, I didn't need that parenthesis. Okay, so when you hit equals, everyone should get that value for top on the top. Hmm?
On the calculator.
Yes, what about it?
What do I put on the calculator?
Like you didn't understand what you put in the calculator.
I put in 6.67.
I'm just trying to accidentally like later.
You got to hit the E button. The E is going to be your times 10 to the thing. That's what it does. So after your E button, you type in the exponent. After you're good with that one, you can go on to the next value. In this case, it's just 1. All right. Then times, again, 5.97. You want to hit the second e function here to the 24th. Then hit equals, and you should get a value here of 3.98199 times 10 to the 14th. That is just the top version. Now, to get what's underneath, all right, once we have what's up top, now you're going to divide by 6.37 e 6. What? You don't even need to hit exponent 2. You can just hit the squared button.
Is it 6.67 or 6.37? 6.67.
6. Well, this is 6.67. This is 6.37. Right? So the radius of the Earth, that is what we're going to use for letter D. So that's why it's on bottom. Big G is this constant value of 6.67 times 10 to the negative 11th. It would be Newton meters squared over kilograms squared. Mass in kilograms here, mass in kilograms here, over meters, and that is squared. So, again, okay, 6.67 e negative 11 times 1 times 5.97 e to the 24th equals, divided by 6.37 e to the 6th squared. And your value should come out to be 9.81. And what would my unit be for force? Any force? Newton. Okay, what is this 9.81? The number should mean something. It's the true value of gravity. Okay, it is the true value of gravity. We use 10 for our calculations just because it makes the numbers come out a little nicer and cleaner. But if you take the universal gravitation constant, you take mass of Earth, radius of Earth, multiply those together, you get this value, which is the gravitational field strength or gravitational acceleration. And all you did was multiply it by 1 kilogram and got this. So that would be like a question, almost the same question as saying, oh, what is the weight of a 1 kilogram mass? Well, another way we could have found this is mg. And if g was that 9.8, you'd be doing 1 times 9.8 or 9.81. You get the same thing. All right, so universal gravitation constant times the planet's mass divided by the planet's radius squared is how you find the value of little g for whatever planet or moon or whatever. Okay, so we will have some problems tomorrow where we're going to be asked to solve for the radius or distance, one of the masses, a force. If you have an object that has, or two objects that have the same mass, you know the distance apart and how much force they're exerting on one another. You could rearrange it and find just m. I gave those equations in the notes. Okay, so I gave those equations right there in the notes from yesterday, which I'm just going to throw up real quick. All right, Newton's universal law of gravitation, rearranged to find just one of the masses, rearranged to find the distance or radius. If the two objects have the same mass, you know the force and the distance. Obviously, big G never changes. You would use this equation. And if they asked you to find gravitational field strength or gravitational acceleration at any one of those points, that would be how you do so, right? Universal gravitation constant, mass of the planet, and the radius of the planet, or D at the bottom. Okay, so now we should be able to flip this over and complete the next couple of questions. Sorry. So for how does your answer from the previous question compare to the force of gravity you would find by multiplying an object's mass by the acceleration due to gravity? Well, I kind of just actually did that, right? If the true value of g is that 9.8 or 9.81, the mass in the first problem, the value of Earth's g, you would wind up with 9.81 newtons. It's the same answer. It's the same answer. Number 5. If Earth had 3 times the radius but the same mass, how would this change the weight of the object? Okay, again, Newton's law, gravitation, mass of the one object, mass of the second object times the constant over the distance between them squared. Big G is a constant, so we're going to pretend like it's not here for right now. So we can take these and kind of set them equal to 1s. Mass of the first object, mass of the second object, distance between them squared. Again, we're making these 1s because we don't know any of the other numbers. And instead of trying to figure out what the heck a new mass would be or double, the mass of the planet, we can just do a simple, quick proportionality type of a problem. Keep them a 1 unless they tell you to change it. They're telling us if Earth had 3 times the radius, so radius will be d, but they have the same mass, how would this change? Well, if neither of the masses change, 1 times 1 is 1, and we would change this to a what? A 3. And remember, like you guys said before, you have to make sure you square that on the bottom. So 1 times 1 is 1, and 3 squared is 9. So it would be 1/9 of the original force. It would be 1/9 of the original force. Number 6. You have a 3 kilogram falling object at terminal velocity. Guys, what is terminal velocity again from the video from yesterday?
Max falling speed.
Yeah, the max falling speed. Its air resistance balances out with the object's weight, so there's no net force. All right, if there's no net force, the object's not going to wind up changing its acceleration, so it's going to therefore be falling at that constant speed. Why they call it terminal velocity? It's like the end velocity, all right, that it's reaching.
Do you know that squirrels can survive a fall from terminal velocity?
No, but now you do. Yes. So what they're asking is, what upward force of air resistance does it experience? So we need to know that terminal velocity will mean that the net force has to equal 0. So if we draw a quick free body diagram, here's our object. What force vector always goes straight down? Right, force of gravity. So Fg. Now, since the F net is 0, air resistance, very good. F sub air We don't know what the values are yet, but we do know that they both have to be equal to each other. They have to be. Absolutely 100%, dude. All right, so what do we got to do? Can we do anything? Yeah, we can. We can figure out what the weight is. Now, I know we were using 9.8 or 9.81 in some of the problems up here, but right now, we're just so the calculations are quicker and easier, we're going to use G as 10 meters per second squared, all right? So to find the weight of an object, mass times gravity, the mass is 3 kilograms, and G, if G is 10, what is the weight? 30 newtons. So 30 newtons down, and air resistance would therefore have to be 30 newtons up. Because they are terminal velocity and the net force is 0, they have to be equal. Okay. So this next problem is similar-ish, but there's one extra kick. All right, just like we did on our tests on Newton's laws, Newton's second law. How do you find the acceleration on an object? You need to know two things. You need to know what the net force is and mass. Good. All right, bet. So they want acceleration. All right, so we don't know either of the velocities, so we can't use one of the kinematic equations. But if we draw a quick little free body diagram, all right, we know that this thing is falling, and it's going to be experiencing a certain amount of weight. It's telling us that it experiences 5 newtons of air resistance. So air resistance is going to go in the opposite direction. So F sub air is going to be 5 newtons. All right, that's fair. Get it? F sub air. Fair? No? All right, sick. Got it. Anyway, what else do we need? All right, to find acceleration, we need to know the F net and M. Do we already have the M?
Yes.
We do. We have it as 2, right? 2 kilograms. What don't we have? Net force. So we have to find net force. Right now, guys, the problem is pretty much telling us we only have 2 forces. We got 5 newtons up, and we have to have some kind of weight down.
So time maybe?
Very close. How do we find FG?
Mass times gravity.
Good. Mass times gravity. What number did we say we were using for gravity? For us right now?
Value for it.
Well, that's the true value, but for our calculations, we're gonna use 10 real quick. All right. So if this thing is 2 kilograms for the mass, and gravity is 10, what's 2 times 10, y'all?
20.
Yes, sir. So this is 20 newtons down. Now, how do I find the net force? Well, if there's 2 forces acting on this guy, and if you have forces in the opposite direction, what do you do with the vectors? Add or subtract? Subtract. So you're going to do 20 minus 5, which is 15 newtons in what direction? So now we can take our F net here and bring it to this spot. So 15 divided by 2. Very good. So this would be 7.5 meters per second squared. And I need one other thing because I know what the direction is, so I have to add it. What would the direction be? Down. Why? Because acceleration is always in the same direction as our net force. Hell yeah. Hey, that's good, guys. That's a solid problem. And me, my stupidness, accidentally put the same question twice. So you're going to do essentially the same question, but we're going to use different numbers. So it's going to be a 12 kilogram falling object experiencing 50 newtons of air resistance. All right, so I guys want you to try that problem real quick. Okay, so guys, essentially the same setup. Okay, you definitely want to draw a free body diagram because it just makes everything visually much easier. We should already always know that F sub g is going straight downward. So we take our mass times gravity, 12 times 10, get 120 newtons downward. There, I told you we're going to use these two values here, 12 and 50. So 50 newtons of air resistance going upward. Subtract the two to get your net force, which should be 70 newtons downward. And to find acceleration, take F net divided by the mass. So the net force of 70 newtons divided by our original mass of 12 kilograms comes out to be 5.83 repeating meters per second squared downward because it goes in the same direction as your net force. Yeah.